So hello everyone, thank you for inviting me. So it will be more a presentation about engineering and startup than science, but I will try to make it interesting for brain specialists as you. So I started the company 12 years ago, just after graduating from École Polytechnique in Imperial College, because I have a family with a neurodegenerative disease, which is called Charcot-Marie-Tooth. So that was my grandmother that has the disease. She had 10 children, and 7 of the 10 children have the disease, so including my father, who gave it to my sister and my brother. So in my family, 2/3 of the people have mobility issues and end up using a wheelchair between 30 and 50 years old. And it's more, it's worse for male subjects. So there is a genetic part that protect women with regard to the family. So when I started, it was the beginning of Boston Dynamics video, very cool video, where you could see robots walking in the snow. And I told myself, okay, so now we have the science to make something, a complex system balance itself. And I want to use this science to make a robot that could help people walk again. So that was the start. So I asked friends from my school. So we started with 5 people from École Polytechnique, and also with Jean-Louis, which is an entrepreneur from the internet era. He founded Télé2, which became a billion-dollar company. And he also has a son which has the same disease, and he was seeking a device to help his son to continue walking. But at the time, we had also competitors when I started, which had already done exoskeletons that were able to make paralyzed people walk. But the problem with the competitors were that they were using crutches to make it walk. So I'll detail more about the engineering part just after. So when we started, my goal was to do an exoskeleton, but without crutches, because in my family they also have the arms that are impaired, so they cannot use crutches. Our competitors have an exoskeleton with 4 degrees of freedom, actuated degrees of freedom, so 2 in the hip and 2 in the knee. So only sagittal movement. So you can only have movement in the sagittal plane, and for everything else, you need the crutches to stabilize yourself. So you use your strength in the arm to synchronize your crutches movement with the exoskeleton, and to stabilize laterally and also forward and backward. So it's very exhausting for the arms. Also, it requires a lot of attention because you don't have, paraplegic people don't have any sensory feedback in the legs, so they don't sense if the device is touching the ground, when it is touching the ground, when it is transferring the weight to the other feet. So it's very hard to learn to use this type of device because you only have a sensory feedback beep that the device is doing to help the user know what is happening. And they also use a lot of the vision to look at their feet and know what is happening. So in reality, our competitors are used only to do a straight line of 100 meters. Then one turn, because it's very difficult to turn, because you don't have any motors to turn, so you have to use to put yourself on a foot in an unbalanced situation and use your crutches to try to turn. So they do only straight line, one turn and straight line. So it's like kind of a device to make exercise. So as you go to the gym, they do that. They go someplace, they use the device, do their exercise by walking, and they go back. So to overcome the use of crutches, we had to develop completely new architectures. So we started in 2013 with the V2, the V1 was only in a drawing, so we never built it. So the V2 is, we built this one. So it's 9 actuators. So one in the ankle, one in the knee, and 2 in the hip. And we built this, and we tried to make it work. So the first work was to make every actuators work together, because you have a lot of sensor, you have a lot of motors, and we need to control them at high frequency. So we have a Ethernet bus that connect every slaves motors, and we control them at 1 kilohertz. So on this version, what we did is to make the system work as a system, to have all the feedback and to be able to control the motors every milliseconds, and to have all the software infrastructure to do that. And we were able to put ourselves in the device, and what we found is that the device was not strong enough to support the weight of someone. It was not fast enough to be able to stabilize everything. So the actuators were not dynamic enough. And we were lacking also degrees of freedom to really stabilize on the lateral side. So with this knowledge, we built the second, the V3, Atalante V3, in 2015. So now we have 12 degrees of freedom, so 2 in the ankles. So we can do like that and this movement, 1 in the knee and 3 in the hip. So we have the 12 degrees of freedom. It's the minimum to be able to stabilize the walk in every direction and mimic the human walk. We also put sensors in the feet. So we have 4 sensors in the feet. We have encoders on each actuators to know the positions of the motors. And we also have inertial measurement unit everywhere in the device. As each generation, we added inertial measurement unit everywhere. So we built this V3. And it was the first version we could use to actually make a walking algorithm. So we partnered with robotic labs, and we implemented the mathematical equation to solve the problem of balance. So it's a high dimension, a nonlinear, very dynamic problem. So mathematically, it's very complex to solve. So we do it offline. We write the big model. We compute the optimal trajectory. It took us at the time around 1 week to compute a solution. It's tailored to someone weight and height. Then we put ourselves in the device and we tried the walk, and we made the first steps at that time. With this device, we did our first clinical studies. So in 2016, M1 pilot study. So we put 1 patient in the device. It was a paraplegic people with a lesion at this level. And so we put a lot of safety around the user. We had the device tethered to a rail. We have a lot of people around. And it was working on valid people, so ourselves. And we never tried it with paraplegic people, so the first time. So we compute the optimal trajectory for the people, for Françoise. We launch the walk, and what happens is that the device is moving like that, but the feet is not going up. So we are like, what is happening? And in fact, when you're valid in the device, you help the device because you are transferring your own weight and helping the device. But with a very really paralyzed people, they have all their weight on the device. So the weight of the user were flexing the structure. And the structure was not stiff enough to support the weight of the user. So in the rigid model, the foot should have lifted like 10 centimeters, but in reality, it was still on the ground. So what we did, we worked 1 week to overcome this problem, and we designed trajectories that raise the feet at 20 centimeters in the rigid model, and it allows us to have real steps. The first step with the Françoise, and the clearance was like 1 or 2 centimeters. So we had a lot of flexibilities, like 10 centimeters of the foot, or even more, uncertainty of the positions of the foot with the user inside. So then, with this knowledge, we designed the V4. So the idea of the V4 was to overcome this flexibility problem. So we we changed the structure to be more stiff. So using a tubular structure to have, because you don't want to be stiffer, but to add weight, because it's a bad cycle. So you want more stiffness, but with less weight. So we have a tube-like structure, like you can see there, for the thigh and the tibia. And we worked also on the stiffness on this part, because what is difficult with exoskeleton compared to robots is that you have the body centered, so you cannot replace the function directly in the axis, so you have to go around. And going around means that you have more flexibilities in your structures. So this part on the hips, you have 3 actuators in the small space, and you need to be very stiff because you have a lot of load. So we built the V4 2017, and we did the second clinical trial. The M4, this time with 10 paraplegic users, and we were able to make them walk like that 10 meters without help, with some stability. It was the beginning, so not great stability, but still they were able to take steps by themselves without crutches. And it works well. But one thing we observed is that the trajectory we computed that were optimal for the users makes the users walk like that. So they were all bent forward, and they were walking like you walk with a big backpack in the back. So that was the optimal trajectory to stabilize the walk. So that was necessary to make it stable, but that was not very beautiful to see. So we thought about this, and what we found is that we have a lot of weight backward, because you have the 6 actuators in the back, and you have also the battery. So the V4, you have the battery in the back. So there was a lot of weight backwards. So to compensate for this weight backwards, you had to lean forward to put this weight in the middle of the feet, because you want to have your weight centered on the feet. So it was a problem. So what we did is we put the battery weight in the back, we split it, and we put it on the leg. So you have the two, now you have the two battery that are in front on the legs, and it add counterweight. So it removed weight from the back and add counterweight in front. And with that, the center of mass of the device is centered on the sagittal plane, frontal plane, sorry. so it doesn't change the weight repetition for the user. So this was the V5 in 2018. So as you can see, it's a very long process because it's hardware. We have a lot of development to do each time. So and with that, we obtained with the V5 you see the first C marking to be able to make the product on the market and to have a device that could make a complete motor paraplegia walk. So we had a device on the market, but we had no market because nobody could buy that. So when we went to see hospital, rehab hospital, and asked them what were their needs, and they had a lot of stroke patients. So approximately 50% of their patients are stroke patients that could benefit from a walking machine to help them relearn to walk. So we changed the function as we develop new functionality on the device to have not 100% assistance of walking, but be able to lower the assistance that the device was providing. So you could have 100% at first and then lower it to 0%. To 0%, the device is trying to make itself forgotten, so it compensates its weight and his inertia and his frictions, but it's still there. And if you lose your balance, it takes over control and keep you safe. So we develop an algorithm to do that. It was so it's the algorithm is like you run 12 degrees of freedom rail. You have to follow the rails, and that's your strength that decide to go along the path. So you have to move each axis in a coordinate way to move along the rail. And if you're too slow, we push you along the rail, because if you're too slow, you will, as it's dynamic, if you're too slow, you will fall sideways. So you have some freedom to do the movement, but if you're stuck, we will finish the steps for you to keep the balance. And then we sold this to hospital, and so this was Talent X. We had to do a lot of engineering to make the platform more reliable, because it's a very complex system. We have more than 27 sensors in the device, 12 actuators, a lot of electronics, mechanics. So what we did, we did 7 million steps with the device in our labs, and we look at what were breaking, what to better the design, to better the safety in the software. And the result of this work was Talent X. So it's like the product-ready version of our work. So it took us 10 years to have a product that could be used by patients and that could have use for stroke patients. So what we've seen is that the device is very useful for hemiplegic patients that are very heavily impacted, so non-walking patients which are FAC 0 or FAC 1 patients. So they just after their strokes, 3-4 weeks after their strokes, they are in a wheelchair, paralyzed, and we can make them walk again. So at first the device is doing everything. But what we've seen, we're doing a clinical study to see with proper data what are the impact on the patient. So we are doing early exo, So it's clinical data with 60 patients to compare standard rehabilitation and rehabilitation with the device. So we have not the result yet, but what we observed is that it's very useful because at first, if you compare to manual rehabilitation, it's very hard to put a patient up again at first, and then you do a very few steps because it's a physiotherapist. So usually you have 3 physiotherapists around the patients, 2 holding him upright and 1 moving the leg with his hand. So it's very manual process, very tiring for the physiotherapist. With the device, we can do 1,000 steps the first session. So we are already putting the user in a position where he's not using his muscles to walk, but he has the sensory feedback of the walk. So weight transfers, vision when you move like that, inertial information about where is your center of gravity and verticality, because for hemiplegic patients, they have a tilted sense of gravity. So for them, the gravity is like that. And by putting them in the device, you give feedback that is contradictory to what they are sensing at the moment. And you progressively tilt the center of verticality back to our normal. Because with the brain injury, they have lost half of their sensory feedback. And by putting them in the device, you put them vertical and doing the right movement. One thing also is that often stroke patients relearn to walk, but in a non-symmetrical way, because we don't want to put weight on the side where they don't sense anything. So they use a lot the side where they sense things, but not the side without too much feedback. And they also have the arm that is impacted. So they cannot do the balancing with the arm. With the device, you impose a symmetrical gait. So they have to have a symmetrical gait and to do the full movement with their legs. So as like that, they can have the right way of walking. So the result of the study will be, we will finish the study in approximately 1 year. We have included 30 patients out of the 60 patients, and we could have real data on what is benefits of using the device for stroke patient. Okay. So as I said in the beginning of the presentation, the goal of the company was to make a personal device to make people walk again in their home or in their community, and to replace the wheelchair. So we continued working on engineering after Atalante, and so Atalante was in 2019, and we did 5 years more of R&D because Atalante has a safety tether, so it's always linked to the rail, not for balance, but just for in case of safety, in case of hardware failure or something like that, you have the safety. And as we are in a hospital, it was more interesting for us to have this safety and to be sure that the patient will be safe than to risk the patients to fall with the device. To do the personal version, we have to overcome this and to get rid of the safety rail. So we developed a new platform. We refined the algorithm for stability. So in December 23, we did a keynote in New York to present the personal device that we have developed. And at this occasion, we filmed a movie in Paris with our paraplegic users, Kevin, which is a T12 paraplegic, and we were able to do a small tour in Paris.
Today, I'm standing. I live in a city that vibrates with life. A city of art, history, science and projects. Projects. I have projects. To turn them into reality, I need to get out and immerse myself in the city. I need to see, sense, breathe, connect. That's what changed my life. Being able to stand or sit at will, to stride, blend with people, wander with my friends, and talk with them at eye level. Three years back, I met Nicolas, who offered, "How would you like to stand up and go for a walk?" At first, I did not believe him. But today, I'm standing.
And now we're in the process of clearing the device for the FDA in the US. So we will start a clinical trial with this device in September with the Veterans Affairs Bronx Rehab Centers in New York. It will be with 15 patients, and it will last approximately 6 months. And then we have to have the clearance beginning of 2026. A very good news also is that Medicare in the US decided to reimburse exoskeletons in April 2024, so just now. So they reimburse the device $100,000, and it's so Medicare in the US is for over 65 people and people with disabilities. So it covers 70% of our target users are covered with Medicare. So it's a very big news for us because it means that approximately 170,000 people will have the device available. So what you saw in the video is our first generation of algorithm versus personal version. So it's done with model-based control. So we write the equation. We solve the problem in real time. We have a regulation to stabilize the walk. So it works, but it's still slow. So as you saw in the video, it's around 0.25 meters by seconds. And we are developing new generation of algorithm with reinforcement learning. So we have it working in the lab. It's incredible the performance we can get with reinforcement learning. So it's black box, it's a neural network. It takes 27 sensors at 1 kHz, and it outputs commands of the 12 motors, and the results are just unbelievable. Like you have really movement, like human-like movement with resistance to push, to perturbation, to slopes, to ground that is when you slide on the ground. And for us, it's very promising because it means that to go into the real environment, into the street where you have slopes, where you could get pushed by someone, etc. It started to become very difficult to do it by writing the equations. The systems were getting very complex. When you add a new scenario, you had to add more complexity to your model. Then you have the flexibility, you have the user in the device. So the model were very, very complex. And it started to become very difficult for engineers to master the complexity of what they were doing. And we were like changing parameters like 200, 300 parameters by hand, by doing experiment, looking at the experiment, changing the parameters. And it was starting to become very complex. But with AI, now it's like we have very good simulation, high fidelity simulation. We worked a lot on making every phenomenon like friction, flexibilities, sliding, etc. In the simulation. So the simulation is very high fidelity, and we train the neural network for 1 week, and then we put it on the device, and it works out of the box. And when you see the device work, it's like what a human would do as reflexes, etc. That's it. So yeah, I'm happy to take any question if we have time.